In this video we're going to have a look at some more standard derivatives, which are special cases, and they also have special questions assigned with them. And the standard derivatives we're talking about are known as the inverse trigonometric functions. So for example, let me take you a straightforward one. If you had y equals, let's say we've got tan to the minus 1 of x, which is the inverse tan function. Okay, now what I'm going to do here basically is not a proof from first principles, but what they will ask you to do is some sort of halfway house proof. And this halfway house proof you need to be able to reproduce, and the result that comes from it, you need to learn that standard result off by heart. So for example, the standard result, as you'll see, is going to be that dy by dx for this is going to be the same as 1 over 1 plus x squared. That's the standard result you need to learn off by heart. And 9 times out of 10 when you use this, you will just quote that result without any proof whatsoever as you do a product rule or a quotient rule or whatever. However, sometimes what they'll do is that they'll ask you the following. So if I just draw a line underneath that, sometimes they'll say, right, starting from y equals tan to the minus 1 of x, can you please prove that that is the case? And when they say prove that's the case, they don't mean prove from first principles. This is the proof that they mean. What they ask you to do is to rewrite that without the inverse tan function in it. In other words, what you can write is that if y is tan to the minus 1 of x, then x is equal to tan of y. Okay, so that is a true statement. If you're not sure about this, think about a statement that you know from your lower schoolwork. So for example, tan of 45 degrees is 1. So tan of 45 degrees is the same as 1. And if you rewrite that as an inverse function, then you'll know that tan to the minus 1 of 1 is 45 degrees. So those two statements are equivalent. One involves the inverse tan and one involves the forward function tan. So that statement there is equivalent to that statement there. So why have we done that? Well, because now if we've got x equals so many y's, what I can do is work out not dy by dx, which is what I'm trying to find, but I can work out dx by dy. So it's just the same thing, but with the letters interchanged. You don't need to worry about this. Why you're allowed to do this comes from proof from first principles, but you don't need to worry about this. You just need to do this process. So dx by dy will be, you just differentiate that with respect to y, And this is a standard result you should have learnt off by heart, and you're allowed to quote it. Differentiate tan, you get sec squared y, like so. So that's what dx by dy is. But if you think about what I asked you to do in the first place, we had y equals that, and we wanted to find dy by dx to be that. So we've got dx by dy, which is the same thing, but upside down. Now, back to what I said before in a chain rule video, even though this gradient function is not a fraction, it behaves like a fraction. And what that means is I'm allowed to flip this upside down as long as I flip the other side upside down as well. So that is a true statement. So dy by dx equals 1 over sec squared y. Now, we've got dy by dx, but as you notice, it's in terms of y. And we want the answer in terms of x's, because that's what the original question was, in terms of x's. So I've got to convert the y back into x. Now, for this, we make use of something that, at the moment, we haven't done it, but it's part of the trigonometric work that we need to know. There is an identity that you need to know. Here is the identity that you will have to learn off by heart for upper 6 trigonometry. And the identity that you need to learn is that 1 plus tan squared is the same as sec squared. Again, when we do the trigonometry, perhaps we'll have a look where that comes from. But that is something that is in your armoury, in your toolbox to use whenever you like. 1 plus tan squared is the same as sec squared. Now we've got sec squared there, so we are allowed to replace that with 1 over 1 plus tan squared y. You might say, well, why have we done that? Well, we've done it purely because Now, if you look back from there to that point there, we know that tan y is the same as x. So this means that we get 1 over 1 plus, and then tan squared means the tan of y all squared, which means x all squared. And so what I've worked out is the following. That if y equals tan to the minus 1 of x, going through this process, dy by dx is the same as that. Now that result there, you need to learn off by heart, but as also you need to learn this process. This is not differentiation from first principles. It is just a process, a halfway house proof if you like, that they do ask about and is likely to be on your paper. Okay, so there you go. That's how you differentiate y equals tan to the minus 1 of x. Now, in a question, if you're dealing with a product rule or a quotient or whatever, and you've got tan to the minus 1 involvement in there, you will not be expected to reproduce this every time you differentiate tan to the minus 1. In a product rule, for example, you're allowed to just quote it. The only time you'd reproduce this is if they ask you to reproduce it. And what they normally do is say, if that is the case, and by rewriting it like that, so they'll give you the starting line like that, they'll say continue on to prove that. So that's what you'll need to do, and it'll be obvious if you need to do this. So 9 times out of 10 you just learn that, or you learn this up here, and then 9 times out of 10 you just apply it. 1 time out of 10 they'll ask you to do that. Okay, so that's the inverse tan. So obviously we've got 2 more functions that you might be familiar with. The second function I'll do is y equals sine to the minus 1 of x. And I'm going to do things in a similar way. And what I'm going to do is this. Rewrite it as x equals sine of y, like so. Then I'm going to differentiate with respect to y. So differentiate sine, you get cos of y. Then I'm going to flip this upside down to get dy by dx. So you flip that upside down and you get 1 over cos y. Now I've got to convert this cos y back into x's now. Well, x is the same as sine y, not cos y. But there is a useful identity again from trigonometry. Now this one you should be familiar with, which says sine squared y plus cos squared y is equal to 1. It doesn't have to be y's, by the way. I'm only using y because I've got a y there. It could be sine squared x plus cos squared x, or sine squared theta plus cos squared theta equals 1. Whenever you get sine squared and you add cos squared at the same angle, the answer is 1. That's an identity you should know. It's one we've already seen in year 12. Right, so what does this mean? Well, I can rearrange this and show you that cos squared y then is the same as 1 minus sine squared y. And so cos y is the square root of 1 minus sine squared y. So cos y is the same as the square root of 1 minus sine squared. Okay, so we'll write this as 1 minus sine squared, like so. And so we're nearly there now, because now we know that sine squared y, sine y is the same as x. So I can replace this as 1 over the square root of 1 minus x squared, because sine y is the same as x. And so dy by dx is equal to that. So this result for y equals sine to the minus 1 of x, giving dy by dx equals 1 over the root of 1 minus x squared, is a result 9 times out of 10 you can quote. So if you're doing a product rule and you have to use differentiate sine to the minus 1 somewhere, you can just quote the result. But now and again they will ask you to go through this formal proof as part A of a question, and then probably in part B they'll ask you to use it to do a product rule or quotient rule. So a very similar sort of technique to the previous one. It's just that they use a different identity to help you get to the final answer. Okay, and then the third one, which you need to know about, is obviously the inverse cos function. So let's see if I can squeeze it in at the bottom here. It's all very similar now. Y equals cos to the minus 1 of x. So x equals cos of y. So dx by dy will be equal to, if you differentiate cos, just be careful, it's negative sine y. Flip it upside down, you get dy by dx, you get minus 1 over sine y. Now, we know what cos y is in terms of x, we've got sine y, so I'm going to use the same identity as in the last question. Sine squared y plus cos squared y is 1. So sine of y will be the square root of 1 minus cos squared. And so sine of y can be replaced with that. Notice, very important you don't forget it, we've got the minus at the front. And then finally, we now know that cos y is the same as x, so change cos y there to x. You get this answer. So there you go. So if you differentiate y equals cos to the minus 1 of x, the standard result you learn off by heart is minus 1 over the root of 1 minus x squared. You need to learn that. So if it's appearing in a product or quotient rule on its own, you can just quote it. And indeed, some of the exercises that are set on A-level questions after this video will be just that. You need to just quote the answer as you're working through it. But now and again, and you'll see this again on one or two of the questions that I set after this video, they'll ask you perhaps to go through this process to get to the answer first before you then use it. Okay, there you go. We've got three different inverse trig functions and how we differentiate them.